have the number of electrons, the protons in the nucleus. This newly charged up atom, ion is its name.
Welcome back. In the last video we talked about nonmetals, semi-metals, and metals, and talked about the physical properties that distinguish them as either metals, nonmetals, or semi-metals. What we're going to do in this video is we're actually going to cover the next dot point, which is all about chemical properties, not physical properties. I read the actual dot point. It says explain the relationship between reactivity of a metal and the likelihood of it existing as an uncombined element. So in this video, or this dot point says reactivity, and reactivity refers to a chemical property. So I'll write the word chemical property. And the actual dot point says we should explain, so explain the relationship. Explain means not just that we have to name it, but name it and say why as well. So I'll go over that soon. Before I start, I want to talk about chemical reactivity. So as I mentioned a second ago, chemical reactivity is an example of a chemical property. And the reason why is because if, for example, let's say we have sodium, and then there is a chlorine close by, these two combine to form sodium chloride, and they combine so that they have reacted. This is chemical reactivity, they have reacted to form a new compound. As opposed to physical properties, an example of a physical property was what we mentioned earlier, melting, boiling, and so melting and boiling points. So for example, if we have H2O in the form of ice, turning into H2O in the form of liquid, while the matter has changed, the state of matter has changed, it's gone from ice to liquid, the actual elements in it are still the same, H2O, ice, and H2O liquid, whereas here we have combined sodium and chloride together to form a new compound called sodium chloride. So this is what I mean with chemical reactivity, two elements or two molecules coming together and forming something new. I'll ask you a couple of questions. So for example, have you ever wondered why H2O is the way it is, like why these elements make up H2O? So we have two hydrogens and one oxygen. But why wouldn't it be, for example, F2O? Why is it H2O? Have you also wondered why, for example, we can find O2 in this form, so oxygen can combine with itself to form O2, but we don't usually find gold in that form. So gold itself is uncombined. It says the likelihood of it existing as an uncombined element, and gold can often be found as just as an AU element, so just by itself. Whereas oxygen, if we find it by itself, is often combined with itself. Or for example, that sodium chloride, why would a sodium, Na, which is a metal, why would that combine with a nonmetal, which is chlorine? So why do sodium and chlorine, why do they combine to form sodium chloride? So I'll answer most of those questions in this video, because it has all to do with the fact that they want to make chemical reactions happen. When in the case of gold, because it's by itself, it's not interested in the chemical reactions, because again, it's happy to be by itself. Because what this actually means is explain the relationship between the reactivity, so how likely it is to combine new elements, or to make new elements, new compounds, of an element, and the likelihood of it existing as an uncombined element. So here we have the periodic table, and if you look at, for example, we've got H2O, right? We've got hydrogen and oxygen here. Hydrogen is here, and it has one electron in its outer shell, and it wants to either have none or have a full shell. In the case of hydrogen, a full shell is 2. So because in this case the first shell can only hold 2 electrons, and we're going to go over this much more in detail in the future videos. But what it can do is it can either give away 1, or take 1, or share 1. And if you look at the actual here, the H2O, what's actually doing, it's sharing electrons, and by sharing electrons, it has reacted. Sharing means it's reacted. And hydrogen is really close to either having a full shell or having no shell. And by sharing electrons, it's allowed to be able to reach that goal, because they all want, every element wants to be having a full shell. So in this case, it's actually reacted to make that happen. Same with oxygen. So oxygen is here, and it has here on the periodic table, it has 6 electrons in its outer shell, called the valence electrons. Now it wants to gain 2 more. So it wants to gain 2 more to have 8 electrons in its last shell, and all the second period ones all want to have 8. So in this case, what it's going to do is going to share 2, one of each of these hydrogens. Each hydrogen shares 1, so it gets 2 from there, and then it's going to have 8 in total. So it has reacted because by actually sharing, it's going to get this 8, and it's going to be happy. Same thing with sodium chloride. So again, sodium was our metal, and chloride was our non-metal. And sodium is here. Sodium is here, and chlorine is here. Sodium wants to give 1 away, whereas chlorine wants to take 1. In this case, sodium has actually given 1 away, and chlorine has taken that 1. And if you look at the actual intro, the intro song, this is what's happening. We have sodium giving 1 to chlorine, and now both of them are happy. So they have reacted to become happy, more or less. Whereas gold is here. Gold is here. And this is something called a noble metal. And that comes from the actual word noble gases. And these here are noble gases. So noble gases are our group 8, and we are going to cover them much more detail soon as well. But all of these have, in the group 8, have 8 electrons. And they have 8 electrons, so they're happy. They're already happy. They don't want to have any more. They don't want to give away. They don't want to take any more. They're happy. So all of these ones here, the ones in the group 8, they're going to stay by themselves. So we can find, for example, argon here. Argon in our air as argon. Not as argon 2, but as argon. We can find xenon or neon all by themselves. Whereas, for example, oxygen, as we said, it wants to have 8. So here we have oxygen, but even as a gas form, it's not by itself. It's sharing electrons with itself. So here it's sharing 2 electrons with itself, and now each of these oxygen has 8. So it's happy. Whereas gold, we said it's a noble metal. This is one of the exception metals, and they actually are happy, even though they don't have 8 electrons. But we're going to cover this in detail later. But these are actually happy as well. The reason why they don't react, the reason why they stay by themselves, is because they're already happy. They don't need to react with anything else to become happy. Whereas the other ones, most of the other ones we mentioned, do. So the exceptions are these noble gases. They won't react. The ones which are closest to having 7, having 8, so these ones here, because they can just give away 1 or 2 and then become and have 8. Or these ones here, because they can take 1 or 2 and get to 8. These ones will be the most reactive. The ones in the middle will become progressively less reactive. So these ones in the middle are less reactive. And some of these metals here, such as gold, are not reactive. We'll cover that in detail later. Whereas other ones like iron are reactive. But so the top one says explain the relationship between reactivity of an element and the likelihood of it existing as an uncombined element. So the more reactive they are, which were the ones here on this side, these metals here, and non-metals on this side, the more likely they are to be found as combined with something else to become happy, more or less. Whereas if they have, if they, for example, have 8 electrons in the outer shell, they won't be reactive, and you can find them as they are by themselves. And then we have certain elements like gold, which are noble metals, which we can also find by themselves. I hope that was useful.
Thank you for watching.